Please begin.
All right. So hi, everybody. I hope your classes today were great, or they will be great if you're in the next session. I'd like to introduce Sabrina, who is our guest speaker today. She is a wonderful engineer who's going to talk about her current project, but her previous work has been doing things like Apple design, and she's got a particular eye for design, which I can appreciate. She's also probably most notably ever a Blue Stamp instructor, a lead instructor in the San Francisco location. So I'll let her talk a little bit about that and a little bit how your experiences here are going to play into what you do in the future. So without further ado, Sabrina, it's all yours.
Awesome. Thank you so much for that intro. I'm going to share my screen now so we can talk about how to innovate, which is what I'm going to talk about today. So as you guys know, I've done a couple different things in my now career so far. But I think this is the one lesson that I love for all of you guys to take home. Let's see, here we go. All right, so the first thing about innovating is that good inventions solve the right problems. So what does that mean? Let's take an example really quick just to level set here. What if someone came to you and said, my bread goes stale because I can't eat it fast enough? So one way to invent on this situation is to look at, oh, my bread is going stale. How can I stop that? So inventor A says, I shall create something that prevents bread from going stale. So that's a totally valid way to solve this problem. Another way to solve this problem is to focus on the second half, saying, I can't eat my bread fast enough. I'm going to create this device that makes bread so fast to eat that bread will never be able to go stale because it's going to be so fast. So that's another way to solve this problem. But the third way to solve this problem is just stop buying so much bread in the first place, right? So whenever you come to any problem with engineering or basically any aspect of your life, really, there are always ways to solve the problem that are more effective than others and potentially address different pros and cons than others. And so I think the core aspect of good innovation and good design is to start by asking the right questions. So that's what I want to walk through today in terms of how I got started with Fix the Mask. So again, good inventions solve the right problems. And to solve the right problems, you need to be asking the right questions. So now we're going to talk about this guy, which is something that's been my baby for the past 3 months. And as you guys are all well aware, there is a global pandemic happening. And basically back in March, there's a lot of headlines out there that look like this. Where are the masks? Global mask shortages everywhere. What can we do about the fact that there's no masks? And what's awesome about this is that innovation started happening immediately. People banded together to create really awesome solutions, and all of them are super valid. So one of the solutions that came off right off the bat was 3D printing masks. And basically it made something that looks like an N95 with a filter in it. That was a really interesting way to solve the problem. Another way is people said, cloth everywhere. Just put cloth over your face, and that's going to help us solve this problem. We don't have enough N95 masks. Let's just use cloth instead. So also another really valid way to solve this problem. The third way, though, is something that I wanted to take a look at and understand what exactly is the real problem here. And so I'm going to go right now through my thought process in terms of how I came up with this invention. So the first thing I asked are, what's the deal with N95 masks? Why are N95 masks recommended in the first place? So I literally just Googled that, and I Googled it and it found, okay, N95 masks are called N95 because they block 95% of particles. So cool. So what? Why does that matter for COVID-19? The next thing I then asked was, how is the virus actually spread? So this is actually a really important point. What I found is that there's an emitter and receiver, and all of you electrical people out there will also appreciate this too. But basically someone spews out virus particles and the other person breathes them in. So what's the nuances of this are the emitter has to aerosolize the particles, and that happens through things like talking and breathing. And the receiver can only get the virus if there's a high enough virus load, meaning there's a lot of concentration of virus in the cloud, and they sit in the cloud for a long period of time. So if you had a cloud of virus, you shove your head in really quick and you leave, it's relatively unlikely that you'll get the virus. But if you shove your head in there and breathe for a while, it starts getting more likely. So after I looked into this and Googled it and I read it, My first question was, what the heck is an aerosolites particle? I had not heard that term before. So I literally just Googled it. And what I found was that aerosolites particles happen when basically they don't have enough mass to drop to the ground. So when you're talking and you're speaking, there's these little droplets of these clouds. And if they're too heavy, they'll fall straight to the floor. And if they are not heavy, then they will actually stay in the air. They don't have enough mass to fall. So they just float, and they float for long periods of time. So that's how you get these virus clouds that are really dangerous. And by the way, all of this is through Google. So it's not like I had all of this knowledge or anything. I'm literally just doing research through the really most basic means. So my next question was, all right, how small do these particles actually have to be? Like for a cloud of virus to be hanging out in the air, how small are those particles actually? And what I found was like, they actually are on the order of 0.1 microns to 0.3 microns. So here I have drawn a virus containing particle as compared to a human hair, but this is obviously not to scale. So to scale, this is actually what we're looking at here. So these particles are so freaking tiny that there is no way that anything that has giant holes in it, in like t-shirts and stuff, is actually going to effectively block out these particles. And that was crazy to me. So that was the first thing I realized, like, okay, this needs to actually block really, really, really tiny particles. So how do we actually do that? So now that I have that, I was interested in how do N95 masks solve this problem already? So what's interesting is that an N95 mask, all it is basically just a net for your face. Like you're putting a net on your face that blocks things out and also keeps bad things in. So you can imagine that if this net had a really, really fine mesh, like, I don't know if you guys strain pasta or whatever, but really, really fine, it's going to make it harder for particles to get inside than if it were like a very, very giant, like soccer ball net. The other thing that's important is this net has to actually attach to your face. If you're holding the net out in front of you, particles can fly in from the sides. And so that was something that was a really key aspect. There's two things that matter here. There's the fit of the mask to your face and the ability for it to filter. So that's what this is saying. Sealing is really important, and also it being able to filter well is really important. And what's interesting is that if you have a well-sealed filter on both people, the virus transmission is going to be significantly reduced, because you basically prevent people from exhaling and having the cloud of virus come into the air in the first place, and you prevent people from actually being able to inhale any clouds of virus because of the seal. So this was a key realization, understanding why N95 masks are so important. So how do N95 masks actually do this? So fundamentally, as we realize these particles are so freaking tiny, how do you make sure that they can't come through like our meshes even that fine? So the answer to this problem is melt blown fabric, which is a crazy awesome fabric that when you look more into it, I'm a nerd for manufacturing processes, so it's actually kind of cool to watch. But in essence, this is what a melt blown fabric is. So you guys are familiar with fabric in general. There's a couple different ways that fabrics are made. You can either do a weave, which is shown in the first picture. You just sort of go over under and cross it over, and that's a woven material. You can knit, which is basically just a series of knots that you tie in a material. And there's also melt blown fabric, which is actually a cool process. I'm sure you've maybe heard that it's kind of like a cotton candy machine, where there's like really high pressure nozzles that squirt out plastic at extremely high pressures. And it creates these really spindly fine strands that you really can't create any other way. And what's interesting is that fabrics, wovens and knits, the smallest diameter of like the finest silk is 127 microns in diameter, whereas melt blown fabric fibers are down to 10 microns. And so the size difference is crazy. There's no way necessarily for us to get even the finest silk fibers to be as small as our melt blown fabric fibers. So that was really interesting to me. And so how functionally does this work? Why is the melt blown fabric so good? So imagine you had two piles of twigs, and your goal here was to prevent getting a ball to drop through to the bottom of your pile of twigs. If you look at these two piles of twigs, which twig pile would you try to drop it in to prevent your ball from falling all the way through? I would pick definitely the one on the right. So basically, this is showing why it's so important to have really, really fine meshes of fibers. If we're trying to block something out or keep something in, you need really, really fine fibers that are stacked on top of each other. And the reason why this is so important is that it prevents the fiber or the particles, the giant balls, from going through the fabric, but it still allows for air to pass through. And that's something that's really important. So I'm gonna go back to this image. If you breathe, like the other aspect of this whole mask design is that you need to be able to breathe while you're wearing it. If you can't breathe while wearing a mask, you will suffocate and die. So all of these are important here. So this is a really cool analogy, in my opinion, for showing that there's a way to block out bad particles while still maintaining airflow. So that was really interesting. Okay, so then I thought, all right, cool. So now I know all of these things. I know how the virus is spread. I know what it takes to actually block out particles of the correct size. Why is there actually a shortage here? So what is this actually stemming from? And it turns out it's stemming from the fact that there's a melt-blown fabric shortage. So this fancy material, this melt-blown fabric, is really hard to produce well at scale. And the reason for that is because it's a very complex process. Because you have to shoot out this plastic at a really high pressure, creates all these spindly fibers. It's hard to make it consistent and consistently well. So exactly, that was that. So all right, now that I know all of this, my next thought is, all right, how can we actually solve this problem? The first is, can we improve the melt-blown fabric process to make it so that it's more consistent? So that's one way. I talked to a bunch of experts about this, and they basically said absolutely not. So there's really no way to make it better. It's a complicated process. It's literally more of an art than a science. And they've been trying to make it better for 30 years, and they haven't been able to do it so far. And that's sort of where we are. So, okay, that path probably still can be done, but it seems like it'll be hard. So to put that one on the back burner. The second thing that we could do is find other materials that can do what melt-blown fabric does. So if there's anything else, it's like a matrix of twigs that actually is able to be so fine and so thin that it could also block out the same type of particles. Now, this one also, I talked to a bunch of experts in this field, and they also said, yeah, that's gonna be really hard. There are alternative materials out there that are being investigated, but going from material concept to mass production takes a long time. So again, this one probably would take a long time. So the third way that I liked the best, which is maybe we should just take our existing supply of melt-blown fabric material and make it substantially more efficient. So if we have one resource in the entire world that can actually filter out particles of the right size, and that's all we have, we need to figure out how to most efficiently utilize that material. So that's where I looked next. And so where else is this material used? It turns out it's also used in surgical masks, among other ways. It's also used in dryer sheets, stuff like that. But after talking to people in the melt-blown fabric field, there's actually one extra nuance, and that is density of melt-blown fabric. So your dryer sheets, for example, are really low density, meaning that you only have like 5 twigs that are stacked on top of each other, whereas the melt-blown fabric inside of both of N95 and surgical masks is like 50 stacks of twigs, like just a giant freaking pile. So then I realized that we had to basically use surgical masks. That was basically our only option. If we needed to have something that was available quickly because we're in a pandemic, that needed to be scalable, it needed to be already in mass production, making better use of surgical masks is the next way to do it. So as you see in this image here, the N95 masks have 4 layers. One of them that actually does the filtration is the melt blown, and surgical masks have the same thing. The other thing that's really cool is that surgical masks are way faster to make. And so this statistic is from March in China. Every single day, 0.6 million N95 masks were made, but 200 million surgical masks were made. So if we could use this material better, more efficiently, we would actually be able to solve the global pandemic. And this got me super excited. Like this one data point alone, I was like, all right, we have a solution here. We're gonna make this work. The cost also is obviously a huge thing. N95 masks right now, if you can get them, are $7.50 a piece, whereas surgical masks are cheap. So this seems like a solution that actually can help a lot of people really fast. So my final question was, all right, so why aren't surgical masks being recommended? What is the problem with them? And the only thing that I could find is that the fit is not good. There's gaps and it's flopping around. So all I did then was like, is there a way for us to improve fit? And that's how we came up with our design. So basically, actually, what's interesting is version 2 was designed and created first, because I wanted it to be like single piece, mass manufacturable, scalable, all the things. But when I actually ideated version 2, I didn't have rubber sheet laying around in my house at the time because I was already shelter in place, but I did have rubber bands. And so all I did was I put a rubber band on my face and I was like, oh, I think this is going to work. And I created it and I made it and I was really excited and I tested it and it worked awesomely. So that's sort of the progression of how innovation happened here. It's not just saying, oh, N95 masks are in shortage, let me just make something that looks like an N95 mask. It's actually understanding the problem. It's understanding every aspect of how is the virus actually transferred. Why are N95 masks good? And all of the extra nuances there. So ta-da, we ideated Fix the Mask, and that's sort of where we are today. So going back to my main initial point, good inventions solve the right problems. And to solve the right problems, you need to ask the right questions. So with that, does anyone have any questions for me? I'd love to chat.
Could you tell us more about your career and your college path as well?
Yes, absolutely. So I will start with college and also my integration into Blue Stamp. So me as a person, I stop sharing. Cool. So I went to college not knowing what I wanted to do. I was interested in marketing. I was interested in medical stuff. I was interested in engineering, maybe. And then I watched this awesome movie called Iron Man, and I was like, ah, that's what I want to do. I want to make an Iron Man suit. And so I went to college thinking that I wanted to be a biological engineer. And I quickly realized that biological engineering is not at all making Iron Man suits. It's a lot more cellular development and understanding how cells grow and all these things that I didn't necessarily care about. So I then pivoted over to mechanical engineering. So that's, I guess, the first lesson is that you can have all of these preconceived notions of what you think you want to be doing, but sometimes you don't know actually what you want to do until you actually do it, and that's totally okay. So that was my first sort of switch. Once I switched and I knew I wanted to become a mechanical engineer, I knew personally that I did not have the background or the type of like mechanical engineering grit that my peers had. Like I had not been building cars since I was 5 or something like that, you know, like I had none of that. I just knew that I liked it and I thought it was very interesting. And so what I did at that point was I threw myself into any mechanical engineering project that I could find. So in college, they actually had these different project teams that offered opportunities to basically build a car or to build an RC aircraft or something like that. And I knew nothing. So I was like, I don't really know what I'm doing here, guys, but let me just help you in whatever I can and see where that goes. And it actually worked out really well for me. I learned a lot really quickly. And so that's the second thing, is to build projects, because all of the theory in the world could be interesting, but you won't actually know what you're doing until you actually go out and do it. And so that actually brings me to Blue Stamp, which is why the program that you guys are in is so freaking awesome. Getting to iterate and do products as soon as possible, understanding how to fail early and fail often is so critical to success in engineering. Theory is cool and really nerdy and awesome, but nothing beats actually building something or making something and then seeing what barriers you have and figuring out how to overcome those. And so my summer as a Blue Stamp engineering instructor was incredible for that, because you guys are all, I'm sure, working on incredible projects, and actually seeing like 15 projects going in parallel and understanding all of the different issues that could come across from things in different industries is really, really valuable experience. And so I think that was one of the formative experiences of my early engineering career that made me fall in love with the engineering process. So that was really awesome. So after my Blue Stamp summer, I worked on my own project for a medical device startup. And I also still had no idea what I was doing, really. I was just sort of failing, making things and failing. But what's interesting is I took that like group of things that I had made and Apple just knocked on my door and said, hey, like, do you want to interview? And I was so confused because I had zero consumer electronics experience. I was not necessarily the top of my class. I wasn't like the best, smartest theoretical mechanical engineer. But what I did in that interview was I took my little batch of things that I had made and I just plopped it on the desk. And I said, these are the things that I've made. This is why they suck. And this is what I would do to fix them. And that in itself blew them away. So a lot of times people come across their desks that are, have the 4.3 GPAs and, took all of the APs in high school and like did all the stuff that, people should do. But what differentiates you is proving that you actually can solve problems. If you actually bring your product to people and show it to them and say, look at the thing that I've done, they cannot negate that you're showing them exactly what they're going to get. Like that, the fact that you are committed enough to produce things to solve problems. And I think that if there's anything that you can take away from figuring out your way through engineering or through getting jobs later on is to show them actual projects you've worked on, how you failed and how you would fix them moving forward. So hope that was helpful.
Are there any other questions? Now's your chance. Sabrina's really smart and knows a lot of things.
Any questions about Apple? Any questions about mechanical engineering or other kinds of engineering? Or
Can you
iron
talk about
suits?
Apple? Every time I ask you about Apple, you're like, well, I can't really talk, but.
Well, I quit now, so I can talk about whatever I want.
I was wondering, how did you test a mask to see if it was efficient or not?
Yes, excellent question. So there's two ways that masks are tested. There's actually three ways that the NIOSH test for N95 confirms that the mask is good for use. The first is it runs it through this like giant filtration test. And all that is basically is it pumps a bunch of salt particles through the mask media at a rate that's really, really high and really, really fast and make sure it passes. So that's the filtration test. There's only one test system in the US that I can actually do that test. And it's basically been completely backed up for the past 3 months. So have not been able to test that side of it yet. But from a fit standpoint, there's actually two ways that fit is confirmed. So, which is exactly what our device does. The first way is basically you have to shove your bag or your head inside of a bag and spray like bitter gas. And if your mask is not sealed well, obviously you'll inhale that bitter gas and you'll have a very unpleasant experience. And that's a test fail. So that is a very archaic method that actually most hospitals use nowadays to test fit. That's one I didn't want to do because I just thought that was kind of inhumane. But it turns out there's actually another way to test fit for using a quantitative system called a Port Account Pro. And that system basically does a ratio of particles inside of a mask versus outside of a mask. And it outputs something called a fit factor, which tells you whether or not you're passing to the N95 standard. So in short, how did I test it? There's a system called a Port Account Pro for fit. And the rubber band system, actually every single iteration that's on our website right now has passed the N95 fit test to the N95 level on at least 5 faces. And it's been hard for me to get a larger sample size because everyone's shelter in place. But I'm working with universities right now to increase the amount of sample size. So that's really cool. The third thing so we talked about filtration, which is that crazy system that doesn't exist readily enough. There's fit. And the third thing is actually carbon dioxide. So this is something that I'm sure you guys have heard recently is that if you wear a mask that's not breathable, you can recirculate the carbon dioxide inside of the mask and that causes problems. And that is true. It's something that's an actual like clinical condition called hypercarbia. You have to be very careful. And actually most N95 masks teeter on the very edge of inducing hypercarbia versus not. What's really cool though about the Fix the Mask solution is that we are totally clean on the carbon dioxide front because surgical masks inherently have that one less layer. So they're still breathable, but they actually still filter well. So those are the ways that we've been testing and we've been successful in all of them so far. So that's really exciting.
Yeah, thank you so much. My name is Anirudh. Sorry, I forgot to introduce myself.
No worries. Nice to meet you. Any questions about life, masks, apples, the fruits, or the
I got a
companies?
question about Apple that I've been wondering.
Yeah.
I'm not allowed to. Before I wasn't allowed to ask you. What's one thing you notice from working at Apple that differentiates the people who just kind of come, do the job, go home, don't really excel at their job, and the people who come in and totally rock it? Like, what is there characteristics that you notice is consistent among those two groups?
I will say that at Apple, everyone is a type A overachiever, every single person. And so it becomes incredibly challenging to differentiate yourself in that route, because everyone is so freaking good there, which is awesome. And it's a place where you can actually really accelerate your career, because you're learning from the best people in the industry. So I'd say that in order to actually differentiate yourself and actually excel within the organization, I would change the question to be like, how do you get what you want out of your experience there? So instead of saying like, what can you do for the organization, think of what can the organization do for you. So the way that I looked about the opportunities there, I saw that the people that like excelled, like went really fast through the management chain of the organization, for firstly that like that's not really done anymore, because it is such a large company. It actually now takes a really long time to actually, you have to have clout and stuff to move forward. But I changed that to be, what am I looking at for my career while I'm at Apple? I wanted to learn how to take things from ideation all the way through to mass production. And that's where I put myself inside the organization. I wanted to be the person that knew how to take an idea and bring it all the way through. And that's, I wanted to do that because exactly for things like Fix and Mask, I wanted to be able to take a product from idea to inception and actually bring it all the way through to the end. So I positioned myself in a spot where I learned everything that I needed to know in order to do that exactly. And so I'd say that even when you go into any company moving forward, don't always get so enamored with, oh, like I need to get a promotion every year and I need to make X number of dollars every year. I think the much healthier way to look at your career is to understand, what do you actually want to learn in your lifetime, and how can each experience that you have teach you one aspect of that so that you can apply it later on. Oh, you're on mute.
Excellent advice for all of our students. So we got 1 minute before the next class starts, so I'm afraid we're going to have to wrap it up. But I'd like to thank Sabrina. Thank you so much for coming and talking to the students. If anybody would like to connect with Sabrina after, if you have some thoughts or you wanted to ask her anything, Brianna or I or Jesse would be able to make the connection so that you can ask her something after the fact.
Yeah,
So,
totally.
Sabrina, thanks again. And for all the students, get hyped if you're already done for the day. Nice work. If you're getting started now, today's website day. Ooh, fun.
I also just put my email in the chat. Please feel free to email me with any questions that you had that I didn't get to.
Yeah.
Cool. Thank you guys so much.
Thank you, Sabrina.
Bye.
Sabrina.